A bicycle tire is a tire that fits on the wheel of a bicycle, unicycle, tricycle, quadracycle, bicycle trailer, or trailer bike. They may also be used on wheelchairs and handcycles, especially for racing. Bicycle tires provide an important source of suspension, generate the lateral forces necessary for balancing and turning, and generate the longitudinal forces necessary for propulsion and braking. They are the second largest source, after air drag, of power consumption on a level road. The modern detachable pneumatic bicycle tire contributed to the popularity and eventual dominance of the safety bicycle. History. The first bicycle tires were iron bands on the wooden wheels of velocipedes. These were followed by solid rubber tires on penny farthings. The first patent for rubberized wheels was granted to Clement Ader in 1868, in an attempt to soften the ride. Rubber tires with a hollow core were also tried. The first practical pneumatic tire was made by John Boyd Dunlop in 1887 for his son's bicycle, in an effort to prevent the headaches his son had while riding on rough roads. Dunlop's patent was later declared invalid because of prior art by fellow Scot Robert William Thomson. Dunlop is credited with realizing rubber could withstand the wear and tear of being a tire while retaining its resilience. This led to the founding of Dunlop Pneumatic Tire Co. Limited in 1889. By 1890, it began adding a tough canvas layer to the rubber to reduce punctures. Racers quickly adopted the pneumatic tire for the increase in speed it enabled. Finally, the detachable tire was introduced in 1891 by Edouard Michelin. It was held on the rim with clamps, instead of glue, and could be removed to replace a patch the separate inner tube attaching to the rim. Three main techniques for attaching a bicycle tire to a rim have been developed: clincher, wired and tubular. Clinchers originally did not have wire in the beads, and the shape of the bead interlocked with a flange on the rim, relying on air pressure to hold the tire bead in place. However, this type of tire is no longer in general use, and the term clincher has transferred to the modern wired-on tire. For the remainder of this article, the modern use of the word clincher will be assumed, in an attempt to provide the best attributes of both wired and tubular methods. Tubular clinchers have also been offered. Clincher. Most bicycle tires are clincher for use with clincher rims. These tires have a steel wire or Kevlar fiber bead that interlocks with flanges in the rim. A separate airtight inner tube enclosed by the rim supports the tire carcass and maintains the bead lock. An advantage of this system is that the inner tube can be easily accessed in the case of a leak to be patched or replaced. The ISO 5775-2 standard defines designations for bicycle rims. It distinguishes between straight side SS rims, crochet type C rims, hooked bead HB rims. Traditional wired-on rims were straight-sided. Various hook, also called crochet, designs re-emerged in the 1970s to hold the bead of the tire in place, resulting in the modern clincher design. This allows higher 80 to 150 psi 6 to 10 bars air pressures than older wired-on tires. In these designs, it is the interlocking of the bead with the rim, not the tight fit or resistance to stretching of the bead, that keeps the tire on the rim and contains the air pressure. Tubular or sew-up. Some tires are torus-shaped and attached to tubular rims with adhesive. The rim provides a shallow circular or outer cross-section in which the tire lies instead of flanges, on which tire beads seat, holding air. Bicycle tires may hold air or not. The ones that hold air do so either with a separate, relatively impermeable inner tube, or between the tire and rim, in a tubeless system. The ones that do not hold air use some kind of elastomer instead. Tubed. A tubed tire has a separate inner tube, made of butyl rubber or latex, that provides a relatively airtight barrier inside the tire. A vast majority of the tire systems in use are clinches. Due to the relative simplicity of repairs and wide availability of replacement inner tubes, tubeless tires are primarily used on mountain bikes due to their ability to use low air pressure for better traction without getting pinch flats. Tubeless tires work similarly to clinches in that the bead of the tire is specifically designed to interlock into a corresponding tubeless rim, but without an inner tube. Air is inflated directly into the tire, and once locked into the rim, the system is airtight. Liquid sealants are often injected into tubeless tires to prevent punctures. Pinch flats are impossible in a tubeless setup because there is no tube to pinch. However, air can escape if the bead lock is compromised from too much lateral force on the tire or deformation of the rim tire due to hard impact with an object. Tubeless technology has progressed significantly over the last few years, and road-specific tubeless technologies for narrow tires are now gaining popularity. Road tubeless. In 2006, Shimano and Hutchinson introduced a tubeless system for road bicycles. Tubeless tires have not yet gained popular acceptance in road racing due to lack of sponsorship, the tradition of using tubular tires, and the fact that, even without the inner tube, the combined weight of tubeless rims and tires is more than top-of-the-line tubular tire wheel sets. Road tubeless is gaining popularity among riders for whom the benefits are worth the costs. Solid. Besides solid rubber tires before the pneumatic tire was invented, solid tires, made of polyurethane or microcellular foam, are also offered for 100% flat prevention. Much of the desirable suspension quality of the pneumatic tire is lost, and ride quality suffers. Airless. An example of an airless tire for bicycles is the high-priced energy return wheel. Other more commercial products are available from Green Tire, Puncture Proof Tires Limited, Kit Ryfan, Trendwizard and Hutchinson. Construction. Bicycle tires consist of a cloth casing covered by a rubber tread. In the case of clinches, the casing wraps around two beads, one on each edge. Casing. Bicycle tire casing is made of cloth, usually nylon, though cotton and silk have also been used. The casing provides the resistance against stretching necessary to contain the internal air pressure while remaining flexible enough to conform to the ground surface. The thread count of the cloth affects the weight and performance of the tire, and high thread counts are generally preferred. The fibers of the cloth in most bicycle tires are not woven together, but kept in separate plies so that they can move more freely to reduce wear and rolling resistance. They are also usually oriented diagonally, forming bias plies. Radial ply has been attempted, but found to provide undesirable handling characteristics. Tread. The tread is the part of the tire that contacts the ground. Compound. The tread is made of butyl rubber that often includes additives such as carbon black, which gives it its characteristic color, and silicon. These additives improve wear resistance, usually at the expense of traction. Some tires have a dual compound tread that is tougher in the middle and grippier on the edges. Many modern tires are available with treads in a variety or combination of colors. Road racing tires with different tread compounds for the front and rear have been developed, thereby attempting to provide more traction in front and less rolling resistance in the rear. Pattern. Treads fall somewhere along this spectrum from smooth or slick to knobby. Smooth treads are intended for on-road use, where a tread pattern offers no improvement in traction. However, many otherwise slick tires have a light tread pattern, due to the common belief that a slick tire will be slippery in wet conditions. Knobby treads are intended for off-road use, where the tread texture can help improve traction on soft surfaces. Many treads are omnidirectional, The tire can be installed in either orientation, but some are unidirectional and designed to be oriented a certain way. Some tires, especially for mountain bikes, have a tread which is intended either for the front wheel or the rear wheel. A special tread pattern, with small dimples, has been developed to reduce air drag. Profile. The profile of the tread is usually circular, matching the shape of the casing inside it and allowing the tire to roll to the side as the bicycle leans for turning or balancing. More squared profiles are sometimes used on mountain bike tires and novelty tires designed to look like automotive racing slicks, as on wheelie bikes. Bead. The bead of clincher tires must be made of a material that will stretch very little to prevent the tire from expanding off of the rim under internal air pressure. Wire. Steel wire beads are used on inexpensive tires. Though they cannot be folded, they can at least be twisted into 3 smaller hoops. Kevlar. Kevlar beads are used on expensive tires, and these are also called foldable. Sidewall. The sidewall of the casing, the part not intended to contact the ground, may receive one of several treatments. Gumwall. Tires with sidewalls made of natural rubber are called gumwall. The tan-colored, natural rubber lacks additives to help protect it from ozone. Skinwall. Tires with very little rubber, if any, covering the sidewall are called skinwall. This reduces rolling resistance at the cost of less damage protection. Variations. Puncture resistance equals. Some tires include an extra layer between the tread and the casing, as shown in the cross-section pictured above, to help prevent punctures either by being tough or simply by being thick. These extra layers are usually associated with higher rolling resistance. Studs equals. Metal studs may be embedded in the tread of knobby tires to improve traction on ice. Reflective equals. Some tires have a reflective strip on their side walls to improve visibility at night. Others have reflective material embedded in the tread. Aerodynamics equals. In addition to the dimpled tread pattern mentioned above, at least one tire has an extra wing to cover the gap between the tire sidewall and the wheel rim, and reduce drag. Indoor use equals. At least one modern bicycle tire has been designed specifically for indoor use on rollers or trainers. It minimizes the heat build-up and excessive wear that traditional tires experience in this environment and is not suitable for use on pavement. Different front and rear equals. Besides the different tread patterns available on some mountain bike tires mentioned above, front and rear tire sets are available for road bikes with different tread patterns, tread compounds, and sizes for the front and rear wheels. Other scenarios involve replacing a damaged tire and leaving the other one unchanged. Self-inflating equals. Bicycle tires have been developed that pump themselves up as they roll forward. Parameters. Sizes. The modern tire size designations, e.g., 37 to 622, also known as ETRTO, are defined by International Standard ISO 5775, along with corresponding rim size designations, e.g., 622 x 19c, Older English, inch, e.g., 28 x 1-5/8 x 1-3/8, and French, metric, e.g., 700 x 35c. Designations are also still used, but can be ambiguous. The diameter of the tire must match the diameter of the rim, but the width of the tire only has to be in the range of widths appropriate for the width of the rim, while also not exceeding the clearances allowed by the frame, brakes, and any accessories such as fenders. Diameters vary from a large 910 mm for touring unicycles to a small 125 mm for roller skiing. Widths vary from a narrow 18 mm to a wide 119 mm for the Surly Big Fat Larry. Balloon equals. A balloon tire, or fat tire, is a type of wide, low-pressure tire that first appeared on cruiser bicycles in the USA in the 1930s. They are typically 2 to 4.7 inches, 51 to 119 millimeters wide. In the 1960s, Raleigh made its small-wheeled RSW16 with balloon tires so it would have a soft ride, like the fully suspended Moulton bicycle. Other manufacturers then used the same idea for their own small wheelers. Examples include the Cooperative Wholesale Society, CWS, Commuter, the Trusty Spacemaster and the Stanningley, UK, made booty folding bicycle. Since the 1980s, tires of a similar width, but full-sized wheels, are used on fat bikes, mountain bikes designed for riding in snow and sand. Inflation pressure. The inflation pressure of bicycle tires ranges from below 2 bars, 200 kPa, 29 psi, for tubeless mountain bike tires to 15 bars, 1,500 kPa, 218 psi, for tubular track racing tires. The pressure rating of tires is usually stamped somewhere on the sidewall. It may be indicated as maximum pressure or inflate to, and is usually expressed as a range. For example, 6 to 8 bars are 600 to 800 kilopascals or 87 to 116 psi. Inflating to the lower number in the pressure range will tend to increase traction and make the ride more comfortable. Inflating to the higher number will tend to make the ride more efficient and will decrease the chances of getting a flat tire. One published guideline for clincher inflation pressure is to pick the value for each wheel that produces a 15% reduction in the distance between the wheel rim and the ground when loaded, i.e., with the rider and cargo, compared to when unloaded. Pressures below this lead to increased rolling resistance and likelihood of pinch flats. Pressures above this led to less rolling resistance in the tire itself, but to larger energy losses in the frame and rider. Bicycle tires are essentially thin-walled pressure vessels, and so the circumferential force in the casing is directly proportional to the internal pressure and to the tire diameter, and the force in the longitudinal direction is half of this. Inner tubes are not completely impermeable to air and slowly lose pressure over time. Butyl inner tubes hold pressure better than latex. Tires inflated from carbon dioxide canisters, often used for roadside repairs, or helium, occasionally used for elite track racing, lose pressure more quickly, because the first gas, despite being a large molecule, is slightly soluble in rubber, and the second is a very small atom which passes quickly through any porous material. At least one public bicycle sharing system, Bixi, is inflating tires with nitrogen, instead of simple air, which is already 78% nitrogen, in an attempt to keep the tires at the proper inflation pressure longer. Though the effectiveness of this is debatable. Effective temperature equals. Since the volume of gas and the gas itself inside a tire is not altered significantly by a change of temperature, the ideal gas law states that the pressure of the gas should be directly proportional to the absolute temperature. Thus, if a tire is inflated to 4 bars, 400 kilopascals, 58 psi, at room temperature, 20 degrees Celsius, 68 degrees Fahrenheit, the pressure will increase to 4.4 bars, 440 kilopascals, 64 psi, plus 6%, at 40 degrees Celsius, 104 degrees Fahrenheit, and decrease to 3.6 bars, 360 kilopascals, 52 psi, minus 13%, at minus 20 degrees Celsius, minus 4 degrees Fahrenheit. equals effective atmospheric pressure equals the net air pressure on the tire is the difference between the internal inflation pressure and the external atmospheric pressure. 1 bar, 100 kilopascals, 15 psi, and most tire pressure gauges report this difference. If a tire is inflated to 4 bars, 400 kilopascals, 58 psi, at sea level, the absolute internal pressure would be 5 bars, 500 kilopascals, 73 psi, plus 25%. And this is the pressure that the tire would need to contain if it were moved to a location with no atmospheric pressure, such as the vacuum of free space. At the highest elevation of commercial air travel, 12,000 meters, 39,000 feet, the atmospheric pressure is reduced to 0.2 bars, 20 kilopascals, 2.9 psi, and that same tire would have to contain 4.8 bars, 480 kilopascals, 70 psi, plus 20%. Rim width. While not strictly a tire parameter, the width of the rim on which any given tire is mounted has an influence on the size and shape of the contact patch, and possibly the rolling resistance and handling characteristics. The European Tire and Rim Technical Organization, ETRTO, publishes a guideline of recommended rim widths for different tire widths. In 2006, it was expanded for allowing wide tires up to 50 mm on 17C rims and 62 mm on 19C rims. Ideally, the tire width should be 1.8 to 2 times the rim width, but a ratio from 1.4 to 2.2 should fit, and even 3 for hooked rims. Tire pressure versus width. Mavic recommends maximum pressures in addition to rim width, and Schwalbe recommends specific pressures. Fat bikes tires of 100 to 130 mm, 4 to 5 inches, width are typically mounted on 65 to 100 mm rims. Forces and moments generated. Bicycle tires generate forces and moments between the wheel rim and the pavement that can affect bicycle performance, stability, and handling. Vertical force equals. The vertical force generated by a bicycle tire is approximately equal to the product of inflation, pressure and contact patch area. In reality, is it usually slightly more than this because of the small but finite rigidity of the sidewalls. The vertical stiffness, or spring rate, of the bicycle tire, as with motorcycle and automobile tires, increases with inflation pressure. Rolling resistance equals. Rolling resistance is a complex function of the materials and construction methods used in the inflation pressure. With higher pressure, up to a limit, thinner casing layers, wider tires, compared to narrower tires at the same pressure and of the same material and construction, larger diameter wheels, and more elastic tread material, all tending to have less rolling resistance. Rolling resistance coefficients may vary from 0.002 to 0.010, and have been found to decrease with inflation pressure and increase with vertical load. A study at the University of Oldenburg found that Schwalbe standard GWHS 159 tires have a CR of 0.00455 for the ISO size 47 to 406. 20 in x 1.5 in, and, for the same model tire, a CR of 0.00336 for the ISO size 37 to 622. 700C. A size to resistance ratio of about -1.8 equals cornering force and camber thrust equals. As with other pneumatic tires, bicycle tires generate cornering force that varies with slip angle and camber thrust that varies with camber angle. These forces have been measured by several researchers since the 1970s, and have been shown to influence bicycle stability. Brands and manufacturing companies. Notable bicycle tire brands and manufacturers include Bontrager, owned by Trek, Chengshin Rubber, also branded as Maxxis and CST. Coca Tire, Continental, Fixation, Hutchinson, Kenda, Michelin, Nokian. Nokian's bicycle tires now owned by Suomi Tires Finland, Panasonic, Schwalbe, Soma Fabrications, Specialized Bicycle Components, Vittoria, Videstein, Wilderness Trail Bikes. See also Bicyclia Gundersi, Outline of tires, Outline of cycling, Fix a flat tire.